Fuel systems. What is a fuel system, and what makes up a fuel system? The fuel system consists of a fuel supply, fuel lines, fuel filter, fuel pump, and carburetor. The most common repair task in the small engine industry involves the carburetor. All carburetors function essentially the same, although there are many carburetor designs and styles. An understanding of carburetor operation in the fuel system reduces troubleshooting and service time. Though carburetors are a major component of a fuel system, they are not always the only component used to mix or deliver a fuel supply to operate an engine. This training module will cover a wide variety of components and subjects that incorporate the many physical parts of a fuel system and the operation of those fuel system parts. You will also learn how and why these parts interact with each other to form a fuel system and deliver the needed outcome in order for an engine to operate properly, and what happens when they are not functioning properly, and their cause and effect relationship to the engine's performance. This training module will cover a wide variety of components and subjects that incorporate the many physical parts of a fuel system and the operation of those fuel system parts. You will also learn how and why these parts interact with each other to form a fuel system and deliver the needed outcome in order for an engine to operate properly, and what happens when they are not functioning properly and their cause and effect relationship to the engine's performance. With the advent of our web-based training site at Briggs Stratton, the Power Channel, we've created a very helpful online course dealing with the complex subject of fuel systems. Because we have a limited amount of time to try and cover the large amount of content available in this module, we'll focus on several segments that are particularly important. Our primary topic of discussion today will be fuels, particularly gasoline and gasoline blends. You're going to learn about the chemical composition of gasoline, the different blends of gasoline, and how the addition of alcohol to gasoline impacts performance and the solvent effect it can have on carburetor parts. The most common fuel used in small engines is gasoline. Gasoline is derived from the fossil fuel we know as crude oil and was originally an undesirable byproduct of refining crude oil. Gasoline is a complex blend of chemicals mixed together to provide a predictable performance when used in specific applications. Gasoline is a hydrocarbon-based fuel derived from the elements hydrogen and carbon. A hydrocarbon molecule is held together by a loose bond between hydrogen and carbon atoms that occurs naturally in all fossil fuels. The energy in gasoline is released through burning in the combustion process. Combustion is the rapid oxidizing chemical reaction in which a fuel chemically combines with oxygen in the atmosphere and releases energy in the form of heat. Combustion produces force that can be used to do work. Most gasoline molecules contain more elements than hydrogen and carbon. For simplicity, a generic gasoline molecule consisting of these elements is identified by the chemical formula C8H18. The formula indicates that a generic gasoline molecule contains 8 atoms of carbon, C8, and 18 atoms of hydrogen, H18. Ignition of a mixture of gasoline and air causes an exchange of elements which releases heat energy. To release energy during combustion, weaker chemical bonds are broken and new bonds are formed. As the hydrocarbon molecule fragments during ignition, oxygen atoms bond with hydrogen atoms. The joining of these atoms releases energy in the form of heat and new chemical compounds. When hydrocarbons are combined with oxygen in a perfect ratio, only water and carbon dioxide are produced. To produce maximum heat energy, sufficient oxygen must be present during combustion. The ratio of atmospheric air to fuel at which the most efficient and complete combustion occurs is the stoichiometric ratio. Although the stoichiometric ratio is theoretically the most efficient air-fuel ratio, it does not produce maximum engine power. A charge with an air-fuel ratio slightly richer in fuel is easier to ignite and generates more useful energy. The stoichiometric ratio for a specific fuel or combination of fuels varies. We express this ratio as the lambda excess air factor, a numerical value representing the stoichiometric ratio of atmospheric air to any hydrocarbon fuel. A 1.0 lambda factor is the theoretically perfect ratio for atmospheric air and a specific hydrocarbon fuel at sea level. For example, a 1.0 lambda factor of gasoline is 14.7 to 1. The most efficient and complete combustion occurs when there are 14.7 parts atmospheric air for every 1 part fuel. We're all very familiar with octane ratings. You're probably even aware that a lower octane rating means that the fuel burns quicker and easier than one with a higher octane rating. It is important, though, to understand how octane ratings are determined. The anti-knock index, or AKI, is the numerical value assigned to gasoline that indicates the ability to eliminate knocking and/or pinging in an operating engine. The more stable the charge during combustion, the higher the AKI. All gasoline is tested and assigned an AKI number using the research octane number and the market octane number. The research octane number, or RON, is the octane number that affects engine knock at low to medium speed. The market octane number, or MON, is the octane number that affects engine knock at high speed and performance, in severe operating conditions, and under load. Octane ratings should not be mistaken as a gauge of gasoline quality. A high-octane fuel may actually cause an engine to run poorly if it is designed to run on a lower-octane fuel. Vaporization is the process in which a liquid is sufficiently heated to change states of matter from liquid to a vapor. Gasoline is very volatile and is blended to take advantage of its propensity to vaporize based on the environment in which it is used. If the ambient temperature is high, the gasoline must be blended to prevent it from vaporizing too easily. If the ambient temperature is low, the gasoline must be blended to make it vaporize more easily. Liquid gasoline is not flammable. Only the vapor emitted from gasoline burns. The combination of gasoline vapor and atmospheric oxygen provides a medium for combustion in an internal combustion engine. Gasoline volatility affects startability and operating performance based on providing sufficient vapor at the correct ambient temperature for the combustion chamber. Industry standards for rating volatility of any given fuel use the distillation test and the Reid vapor pressure test. A distillation test is a test for determining the composition and volatility characteristics of the components of a given fuel sample. A distillation test is performed by boiling a fuel sample and measuring the rate of vaporization. Boiling points of various gasoline blends are recorded from initial boiling to complete vaporization of the entire sample. Time and temperature results are plotted on a graph. The initial boiling point of gasoline ranges from 85 degrees Fahrenheit to 105 degrees Fahrenheit. The temperature at which the first 10% of the fuel sample evaporates indicates how well this particular blend of fuel reacts when starting in different temperature spectrums. The first 10% of the vaporization indicates the rate of vaporization for the fuel sample. The Reid vapor pressure test, or RVP, is a test used to determine the pressure produced from the vaporization process. In the test, a glass vessel or bomb is cooled to 32 degrees Fahrenheit. Fuel is poured into the vessel at a temperature of 32 degrees Fahrenheit to 40 degrees Fahrenheit. The glass vessel containing the fuel is immersed in 100 degree Fahrenheit water. The vessel is removed every 2 minutes and shaken to promote vaporization. A measurement is made at the accumulated pressure after shaking of the fuel produces no additional pressure increases. The RVP test provides a base number identifying the tendency of the fuel to vaporize and the pressure produced. Gasoline blended for summer use has an RVP of approximately 8 psi at 100 degrees Fahrenheit and approximately 12 psi or more at 100 degrees Fahrenheit for winter use, according to the expected temperatures in that geographical region. Gasoline with an RVP in excess of 12 psi is used in the severe weather in the northern climates. Ambient temperature is the main factor in selecting the proper fuel volatility. For example, using gasoline blended for summer in a cold environment results in hard starting. This occurs because the gasoline has been blended to vaporize at higher temperatures. And at lower temperatures, less vapor is available per unit of gasoline. In addition, cold air is more dense and contains more oxygen per unit of air, causing a leaner air-fuel mixture. Although the engine may have ample liquid gasoline in the combustion chamber, there is a minimal amount of vapor available in cold winter temperatures. The engine is more difficult to start because of the lack of vapor and lean air-fuel ratio, despite the presence of the liquid gasoline in the combustion chamber. Using gasoline blended for winter use in the summer can result in the fuel vaporizing too rapidly. This can form undesirable vapor bubbles in the fuel system, resulting in vapor lock. Vapor lock is the stoppage of fuel flow caused by internal pressure of a fuel vapor bubble that equals or exceeds the ambient fuel pressure. All gasoline contains vapor bubbles. Vapor bubbles are caused by agitation, heat, and fuel volatility. In normal conditions, the fuel system of an engine passes vapor bubbles without a problem. However, an increase in agitation, heat, and/or fuel volatility can cause restrictions by vapor bubbles at critical points in the fuel system. Restriction of fuel flow occurs as a result of pressure differences in the system. Vapor bubbles have a measurable internal pressure that determines the size and rate of expansion. When the internal pressure of the vapor bubble equals or exceeds the pressure of the fuel, fuel flow stops. The most common areas of vapor bubble fuel restriction are the small orifices of the fuel system, such as the pilot jet orifice. As fuel flow is slowly restricted by growing vapor bubbles, engine temperature increases from the leaner air-fuel mixture. Fuel temperature also increases with engine temperature, adding to the problem until vapor lock stops the engine. Reformulated or oxygenated gasoline, also called RFG, is gasoline that contains chemical additives to increase the amount of oxygen present in the gasoline blend. In 1990, in the United States, President Bush signed into law the Clean Air Act of 1990. This act mandated that gasoline used in the non-attainment zones must contain an additional 2.7% of oxygen by 1995. The classification of non-attainment zone was based on the carbon monoxide or CO levels in a geographical region during the winter. Reformulated or oxygenated gasoline was introduced to reduce all CO emissions of all gasoline-powered internal combustion engines. Additional oxygen in the gasoline brings combusting efficiency closer to the stoichiometric ratio. Oxygen was added by blending oxygenates into the gasoline. The most common of these fuel oxygenates is alcohol. Alcohol is a fuel, or fuel additive, used to enhance the octane rating of gasoline. In the 1970s, ethyl or grain alcohol was used as an alternative fuel and renewable energy source. The addition of alcohol to enhance octane ratings proved to be an inexpensive method of increasing overall performance of the gasoline. Alcohol mixes easily with gasoline without the use of an additional blending agent. Alcohol burns with less BTUs than gasoline. A 1.0 lambda factor for alcohol is 9 to 1, and it has a richer air-fuel ratio than 14.7 to 1 for gasoline. The addition of alcohol provides more oxygen, resulting in a leaner overall air-fuel ratio. This produces increased combustion chamber temperature, combustion gas temperature, and overall engine operation temperature. The oxygen content of alcohol affects the oxygen present in the air-fuel mixture. Alcohol has a high affinity for water and absorbs water from any substance that it contacts, including air, rubber, or other material in the fuel system. For example, a water bubble found in a fuel tank is not always caused by a defective fuel can. A water bubble can be formed from alcohol in the fuel combining with humidity in the air. This increased amount of water in the fuel system tank will cause corrosion for metal parts such as fuel tanks or carburetor parts. The higher percentage of alcohol in the gasoline, such as E85, and the increased amount of water will mix to become a glycol-type jelly in the fuel system and become extremely caustic. This caustic chemical will attack the metal parts, resulting in carburetors to become corroded. When the glycol dries out, it leaves behind a white powder-type substance that is the remains of some of the metal compounds being leached out of the carburetor's body and bowl. This can also be referred to as oxidation, or in the case of steel parts, rust. The end result is that the carburetor will not perform to its fullest potential for the engine. We all know that alcohol isn't the only thing that can have a serious impact on an engine's performance and lifespan. Dirt and debris ingestion remains one of the main culprits of engine failures. Briggs Stratton has always required the use of fuel filters on its engines. In fact, most Briggs Stratton fuel tanks come equipped with built-in fuel filters. Fuel filters are rated by the size of debris that it will let pass. This is measured in microns. To give you a frame of reference on micron ratings, an average human hair ranges from 40 to 300 microns in diameter. These ultra-fine filters will stop most dirt and debris from entering the carburetor, providing just one more level of protection against harmful ingestion. Although we did not review all the areas of the fuel system, we touched upon several that should offer you some insight as to how you can use the content of the Power Channel e-learning site in diagnosing and troubleshooting carburetor-related performance issues. There's a great deal of time, effort, and information compiled there aimed at helping you to become more informed and knowledgeable about Briggs & Stratton products. We hope it meets your needs, and we look forward to your feedback so the system can be fine-tuned to make it even more helpful.